there's going to be a theory section, but I think it's only about two slides. We're going to focus on going through examples of mixed effects modeling, just representative, mostly simple examples. And mixed effects modeling is very, very complicated, and there's a lot of, it can get wild. We're going to just keep it simple. This is supposed to be an introductory, maybe first look. All right, so I'll go ahead and get started. There's, like I said, I think 2 slides of theory, just to see what the difference is between mixed effects modeling and ordinary linear modeling. So an ordinary, general, multiple linear model would be written typically like this. You have the ith response value is equal to some intercept plus some linear combination of coefficients times explanatory variables. And you don't make any assumption about what those coefficient values are. You don't assume that they're randomly drawn from any sort of distribution. They just are what they are. And that's the expectation of the response. But any given actual observation or measurement is going to have some sort of normal error tacked onto the end that kicks it off of the plane where it otherwise would be. So yi is expected to be on a plane determined by this linear combination of the explanatory variables, but it gets kicked up or down by some error value. And we generally will assume that those errors are IID normal. So a lot of the text here is just for your own future reference. I think the better thing is to try to listen to my explanation than to read all of the text. So when you're doing this type of modeling, the maximum likelihood estimator is also the least squares estimator. It's the set of coefficient values that result in residuals that have the smallest possible sum of squares. And that's a very straightforward, closed form answer to what's the maximum likelihood estimator. And also inference turns out to be very simple for estimating or for finding confidence intervals and asking hypotheses or testing hypotheses regarding the coefficients. Okay, now you might, rather than just assuming you don't know anything about the coefficients, you might assume that some of the coefficients have some distribution that you could actually bring into your model. And a nice assumption is that, well, maybe they are drawn from some normal distribution. So, and it's hard to think about this in the abstract. It's going to be a lot easier when we see the specific examples. So here's everything we already had. We've got potentially fixed coefficients without any assumption. These are just parameters. There's no assumption about a distribution. We don't know what they are. We don't make any assumptions that we know what they are. And we've got some corresponding explanatory variables that they're multiplying. We've got our error, but in between, we've got these extra terms and extra explanatory variables where the coefficients we're going to build some sort of assumption about the distribution of those coefficients. And in this case, you can do maximum likelihood estimation, sort of. It's much more complicated and it doesn't have a closed form solution, and people will use iterative algorithms like EM, expectation maximization. And I should warn you that this is not a convex optimization in general. So you can miss the solution. You can get an answer that's actually a local maximum but not the global maximum, and it's hard to know whether that's happened or not. That's That's one reason why plotting and sort of sanity checks are actually really important for mixed effects modeling, in my opinion, because you just don't have really a guarantee that you didn't land in a local maximum. Anyway, we'll see. We'll talk about that a little more later. And inference tasks are much more complicated. So you don't just have a straightforward way of calculating the p-value for the assumption that the b's are 0, or even that the betas are 0. Once you include the b's, you have to make approximations. So people disagree on what approximations to make, what method of hypothesis testing to use, and whether it's even legitimate. And we'll see that in a second too. And by the way, these epsilons don't actually have to be independent of each other. That's usually the assumption for linear modeling, but actually in our final example, we're gonna have errors that aren't independent of each other, and we're still gonna be able to deal with it with mixed effects modeling. All right, so that's the end of the theory. But hopefully the examples are supposed to clarify or give you some, a better conception of what this looks like in practice. So here's the first example. We're gonna have some number of females and some number of males who are going to have their blood pressures measured. And each group has its own mean. Let's see, I'm calling them mu F and mu M. Each group has its own mean. And the ordinary way of thinking about this for the first stat class is just, you can do like a t-test or something. You say, well, the female measurements are from some normal distribution centered at mu F with some variance sigma, some standard deviation sigma. The males are going to be draws from another normal distribution with its own mean, mu M, and its own variance. Well, maybe often you'll assume it's the same variance. You can do it either way. And that's an ordinary t-test scenario. But we're going to have a little bit of a difference in this case. If you want to write it as a ordinary linear model, you might say let mu F be the intercept and let the difference between mu M and mu F be the coefficient of the indicator variable for males. And then you've got a normal error. Okay, now we're going to have a difference in that each subject's blood pressure is going to be measured multiple times. Now, we talk about people having a blood pressure, but really if you measure your blood pressure at one time and then you measure your blood pressure a couple hours later, you're going to get different readings usually, because blood pressures just vary over the course of the day and the week and the month. And that doesn't mean that you don't have an expected blood pressure, like a baseline blood pressure. So how would you incorporate that information if instead of each male and female in the study having their blood pressure measured once, they have their blood pressure measured, let's say up to 4 times, 1 to 4 times? Well, you can't just treat all of the measurements as if they were IID draws from the same distribution, because 2 measurements from the same person are obviously going to be correlated. And one way of trying to deal with this type of scenario is to assume that females have an expected blood pressure. Males have some expected blood pressure, but any given person, any given female, let's say, her blood pressure is going to be, her baseline blood pressure is going to be some standard deviation, some normal draw away from the female expectation. So the female expectation, I think I put 112. I made up numbers for these examples. The expected female blood pressure may be 112. Now, a particular female may have a baseline blood pressure of 120, and she deviates from her group's expectation by 8. And another female maybe have 111. She deviates from her group's expectation by -1. And you might just say, I've got all of these females brought into the study and their baseline blood pressures, I'm going to pretend that it's reasonable to think that those are normal draws, normal deviations from their group expectation. So each female has a baseline blood pressure. The actual measurements of the person's blood pressure are not that number necessarily. They could be, but they could vary. Like I said, you take someone's blood pressure in the morning, you take it in the afternoon, and it may vary by 10 points. I actually don't know what the units of blood pressure are. So so you've got, let's see if there's anything else on this slide. Okay, so this can be modeled by mixed effects modeling. So what does that look like? Here's the ordinary linear model where I've got the intercept is the female expected blood pressure. This coefficient is really the difference in male and female expected blood pressures. There's an indicator variable. If the ith person is a male, then, well, let's just say in a particular case, the ith person is a male, then these first two terms just simplify to mu-m. But you can also incorporate the fact that different people have their own expected blood pressures that deviate from their group by some normal amount. And then their actual measured blood pressures are an error away from their expected blood pressures. So, and this is a little bit complicated. I'm not going to go through the model for every single one. There are slides for the model for every single one of these. It's just to show you that each of these models actually does fit in the general framework that I described a few slides ago. I've got a little section here where I've got an indicator, but this is the formal way of doing it. The simpler way of doing it is to say that if subject I, if blood pressure measurement I came from subject J, then the value of blood pressure measurement I is just going to deviate, is a normal error away from that person's expectation, and that person's expectation is the group expectation plus their individual subject deviance from the group expectation. If you want to think about how to write that out in terms of the general formulation of mixed effects modeling, it has to do with inventing these indicator variables, telling you which subject you are, or which subject observation I came from. But I don't want to necessarily go into that. The thing to look at is to go straight down here and you say the ith blood pressure measurement, say, assuming that subject I is a male or the ith blood pressure measurement came from subject J, who is a male. Then you've got the male overall expected blood pressure plus the deviation corresponding to subject J, that was a normal draw with mean 0 and some unknown variance that I think I called it sigma s, plus some other error that corresponds to just any given blood pressure measurement deviating from the person's expected blood pressure measurement, because that's just how blood pressure works. All right, here's the diagram of the situation. If that wasn't clear yet, and even if this isn't clear yet, then we'll continue talking about it when we switch over to our R script. All right, there's a female expectation. All right, there are some number of female subjects who get brought in. Every female subject has an expected blood pressure that differs from her group's expectation by some normal draw, called a subject effect, B1 through Bn, IID, normal, 0, sigma s squared. So there's some variance that's associated with the normal distribution that's generating the individual females' expected blood pressures. And they deviate from their group's expected blood pressure. Now, person 1, subject 1, a female with expected blood pressure μF plus B1, maybe she has 3 blood pressure measurements. Each one deviates from her expectation by some error, epsilon 1, epsilon 2, epsilon 3. And these are the things, this whole sum of group expectation plus subject effect plus error, that sum altogether is what we're thinking of as the responses that we're going to see, Y1, Y2, Y3. So they're measurements. Huh. All right, so we're going to look at the R script now. So mixedeffects.r. And we're going to simulate data according to the mechanism I've described. Actually, the first thing we're going to do is read in a couple of helper functions to do the simulation and to do some plotting for us. So I wrote some code. So make sure you do Control Enter is for this one. It's going to read in a file that I've got on my website. Control Enter, read in that file I've got on my website. Okay, so let's pick some specific values for this scenario, the blood pressure measurement scenario I've described. Let's say that the female expected blood pressure, let's say systolic blood pressure, and again, I made these numbers up. I, don't think that these are exactly realistic. Just pretend the expected female blood pressure is 112. The expected male blood pressure is 128. And we're going to have 5 female subjects, 6 male subjects. Their actual blood pressures, their blood pressure effects, their deviations from their group averages are going to be normal draws, mean 0, standard deviation 7. Okay, n.rep. This is going to represent the number of measurements for each individual being studied. And so I wrote 1 to 4. That's my function. My simulate function is going to take that and draw anywhere from 1 to 4 uniformly blood pressure measurements for each person. So another nice thing about mixed effects modeling is that you don't have to have balance. There's really no benefit pretty much to having the same number of observations per person or per group. That's a big, in other ways of trying to deal with repeated measurements. There are more old-fashioned ways of dealing with it, and if you didn't have the same number of measurements per group or per person, it just was horribly messy and possibly impossible in some cases. So that's not really a concern.
Can I ask a question?
Yes, go ahead.
Is that, do you think, the main advantage of mixed effects modeling over within repeated measures ANOVA? If you have categorical variables?
I think it's one in, let's see.
Would you consider repeated measures ANOVA one of those old-fashioned ways?
Yeah, I would. I mean, it's not really super old-fashioned. People still do it, but I think it is a major benefit. Furthermore, if the normality assumption is reasonable, then you also have the benefit of just building. If you build basically anytime you build correct assumptions into your model, your inference and estimation is going to benefit from that. So if you don't assume if it's reasonable to think that every female's expected blood pressure is some normal deviation away from the group's expected blood pressure, which is very reasonable. It's very reasonable to think that. I mean, maybe it's not exactly normal, but in reality, things tend to be, normal in biological systems. So I actually think that there are various advantages that people list, but I think just the idea of building a reasonable assumption into your procedure and making making use of something accurate rather than just saying, I don't know anything about about female expected blood pressures. Every female has their own expected blood pressure, and I make no assumption about what the distribution is. That's just so you're not benefiting from incorporating a reasonable assumption, and you're losing a lot of the power of, for example, hypothesis testing. All right, so that's my take. You can find lists on the web of people uh, with providing their own opinions and for the advantages. Usually, of course, if you're making assumption, if you're bringing to bear an assumption that's not reasonable, then you might be you might end up doing worse. Um, all right,
Also,
but
there
yeah,
is a question in the chat box. Can you repeat the difference between sigma.s and sigma?
sure. So any given female has an expected blood pressure. That's their underlying sort of baseline blood pressure, and the particular times when you put the strap on their arm and get a readout, it's not going to be the same from 1 hour to the next. It's going to vary around some sort of baseline expected value. And of course, the expected value changes over time. A person can develop higher blood pressure, but that's not what we're talking about when we just sort of think about a person who has their blood pressure measured once and then an hour later it's 5 points higher or 10 points higher or something. That's not like they developed high blood pressure. That's just like there's a natural variation in a person's blood pressure when measured at random times throughout the day. So the the female's expected blood pressures are not equal to the overall female expected blood pressure of 112. I'm saying they are a normal draw away, and then that normal distribution standard deviation is 7. And then any given particular person, let's say Sarah has a blood pressure of 120. Okay, if you take her, that's her underlying expected blood pressure. If you actually measure her blood pressure 3 times this week, it's not going to be 120. Maybe it will be, probably it won't be. Probably it will vary around 120. And those deviations from 120 are the errors and the normal IID normal errors, and that distribution has standard deviation sigma. So there has to be 2 different standard deviations involved here. There's the standard deviation for generating the people's baseline values, and then there's the standard deviation for generating the actual the actual measurements that vary around a person's baseline value. Now keep in mind here, I'm doing a simulation. In general, you don't know sigma.s, you don't know sigma, you don't know the true expectations. So I'm just doing a simulation because I want us to be able to compare. I want us to do the fitting and be able to compare the truth. Okay, don't. I didn't realize this plot was up. I wish this wasn't up. We're looking ahead to a different example here. I want us to be able to, for the sake of understanding what's going on, think about simulating the data, and for the sake of trying to assess how well these mixed effects modeling functions work, to be able to compare the estimates to the truth that we know because the data was simulated. And originally I had these all the data simulation in this file, but it was just the file was insanely long. So now they're all in. I've got functions written. If you look up at the top, you could download this if you want. If you just paste this URL into your browser, and you can download this R file and see the functions that are simulating this data. But it's just simulated according to the mechanism that I just described. And we're not going to look at that. We're not going to worry about the details of simulating the data. We're just going to call simulate RM, repeated measures. Okay, so I'm going to run this chunk, and now I'm just going to type S so that you'll see what got returned by my simulation function. Okay. Here's the data set. You've got subject 1, apparently only had one blood pressure measurement, and it was a 101. Subject 2 had a 100. Subject 3 had a 104. Subject 4 had a 123 and a 129. And they're in groups 1 and group 2. So my function doesn't give these descriptive names because I want it to be something that you can think, you could play around with these functions and simulate your own fake data sets and see how things work. So I'm going to give more descriptive names for our specific example. Blood pressure, subject, number, and sex. All right, so here's our data set. We're measuring blood pressures of some females, some males, and some people had more than one measurement. This person, subject 5, had 4 measurements. All right, and I've also got some plotting functions that are in the other file. See this mixed effects plots? If you want to look at these plotting functions and maybe adapt them to suit your own purposes, for example, then you can just download them from my website. So here's there's no data on this plot. This is a plot that is showing you the truth. There's a true female expected value. There's a true male expected value. And the subjects themselves, subject 1, subject 2, subject 3, subject 4, subject 5, their individual expected values deviate from their group's expected values by some normal draw. All right, so person 1 is a little less than her group's average. Person 2 is a little more. Getting flooded with chat here, but I don't know how to see the chat. I'm hitting.
The question is what happened at line 33?
33, right? Simulate RM. This is a function that's taking care of what you're seeing in these plots. All right, so I'm generating a data set. Here's the data set. This came out of simulate RM. I gave my function 2 group expectations, a number of people per group, a standard deviation to use to generate the people's expected values, which are their deviations from their group expected values, number of repetitions, number of measurements to take per person, and a standard deviation to use in generating those actual measurements. That the sigma is going to be used to generate the deviations or the errors from each person's expected value. All right, so, and in this first plot, what we're seeing are the group's expected values. And again, simulate RM, let me just clarify, simulate RM, that function is defined in this file. So if you run source of this file, then you've brought that function into your environment. And if you download this file, you can inspect the code and see exactly what this function looks like. But I just, for the sake of focusing on inference and model selection and estimation, we're not going to go through all of the code of actually generating it. This file, believe me, this file is long enough as it is. We're not going to focus on actually writing the code that simulates all these numbers. The function simulate RM generated this data set according to the mechanism I described. There are group expectations, there are individual deviations that need to be drawn from those group expectations, and then there are measurements of those individuals that are going to differ by normal deviations from the individual's baseline expectations. All right, so there's no data here, no data on this picture. There's one group, there's the female blood pressure expectation and the individual subject's baseline blood pressures that you will not see in a data set. And then here's the male baseline blood pressure. Remember, these I defined up here. And then the simulate RM drew some individuals. All right, and I'll just, if you're really curious, when we looked at S, it had an X, that was the data set. It also, it returned something else called subject.effects. And those are these sort of deviations from group means that you're seeing here. That's how I know the true people's, I know these individuals' true expectations because Simulate RM, it generated them and it sent them back along with the data set. All right, so here are the group expectations. Here are the individuals' expected blood pressures. And this is all pre-data. Now, what happens when their blood pressures were measured, or in this case, generated, simulated? All right, so I've got some new dots in here. This this lady had an expected blood pressure of 108 or something, and her actual observed blood pressure was 3 units less than that. And similarly, every person has an expectation, and their actual observed blood pressures deviate from their baseline blood pressure by some normal draws. Okay, and the next plot is just the more realistic picture. In reality, you don't know the group expectations, you don't know the individual's expectations, and your data could be visualized more like this. You see, this is all you see. You take these measurements of individuals' blood pressures, and you might see something like this, and you say, well, there's a female group average and a male group average, and maybe I want to estimate them, maybe I want to test whether or not the groups have a difference in their expected blood pressures, but I've got repeated measurements, and this is the kind of data that I'm dealing with. So we're going to use a function called LMER. All right, so if you don't have LMER test, which you probably don't, then you need to highlight install.packages, LMER test, and do run to install the package, and then do library. I'm just going to go ahead and skip to library to get this function onto your computer. To get the package into your onto your computer, and then get the library into your environment. So it's kind of like LMER. It's kind of like LM. We've got a formula, comma, a data set. But in this case, you have the option for LMER, you have the option of including some terms that are random effects. So we're saying sex is a ordinary, it's not in parentheses. That means for LMER, that means it's a fixed effect. Every sex has its own expected blood pressure in our data set. But each subject gets their own random effect for intercept. Each subject, so we're not saying each subject has their own intercept, because we've got parentheses. The parentheses means that each subject gets their own intercept. The one means intercept. You could have each subject could get their own coefficient of some other variable, and you would have that other variable right here, and we'll see an example of that later. But if each subject gets their own random effect where they deviate from the intercept, from their group's intercept, then this is exactly the formula that you need to specify to fit that model. All right, so hopefully everyone has their package installed, and I'll go ahead and run this. All right, so I've fit the model. I've got parameters now. And in particular, I've got fixed effects. So the fixed parameters are, well, they're going to be an intercept and a coefficient of males. And here they are. There's an intercept, 109, and really that represents the female's expected blood pressure, overall expected blood pressure, and the sex M coefficient represents what you need to add to that value to get the male's expected blood pressure. And so I'm going to give these, I'm going to go ahead and define more descriptive variable names. Mu.f.hat, that's just the first value here. Mu.m.hat, that's the first value plus the second value. And those are the, those are the estimates of the female and male overall expected blood pressures that came from this data set.
We have two questions just about package. One, actually, it might have been here for a bit, but I didn't see it. Just asking if you could say a little bit more about the package. I assume meaning LMER. Or,
is there anyone who's having trouble installing it, or is this just about?
No.
Okay.
Well,
sure.
And then the second question is the one line subject, the function for this package. I think just asking for some to clarify just the syntax you use for a random intercept.
Well, I will comment on the packages first then. So LMER test, the original package is called LME4. And you'll notice if you installed, or even if you did the library of LMER test, oh, I already had it read in. But you'll notice that it brings in a package called LME4. And that's the original package that was very common for doing linear mixed effects modeling. LME stands for linear mixed effects. That's really, people aren't too careful in the terminology here. So mixed effects, usually they mean linear mixed effects, and that's what I am describing in this workshop. But you can do nonlinear modeling and you can do nonlinear mixed effects modeling too if you really, really get complicated. So LMER really is from the LME4 package. That package does not tell you when you do the, so you can do summary of M. I think I'm probably doing it down here. Summary of M. If you do summary of M without doing LMER test, just by bringing in LME4, you can still do LMER, still do the fitting, but the summary function does not give you p-values. This is along the lines of what I was saying earlier, how hypothesis testing in the context of random effects or mixed effects modeling is actually controversial. The original author insisted that he didn't want people to believe p-values in mixed effects modeling, essentially. But people just wanted p-values, so they came up with what they consider reasonable approximate tests, and so that's what people use reasonable approximate tests now. And if you want to see p-values that will generally be accepted by practitioners, then you need to go a little above and beyond the LME4 package. So LMER test automatically, it's going to bring in LME4 automatically, and it's going to, for one thing, show you p-values when you do your summary of your model. Now, in terms of the syntax, I think it's best to just see some examples. I think it's best to just start by thinking about this scenario. I've got groups, and in this case it's sex, and I've got people, I've got sort of objects within each group, and I've got repeated measurements taken from those objects. Well, this is what you do. You have the fixed effect group. Each subject needs their own deviation from the group expectation. Each subject has his or her own expectation, and it deviates by some fixed amount. It doesn't, you could have another variable here if every subject had their own, let's say, different slope, had their own coefficient for that variable. But because we don't have, we're just saying every subject has their own effect. They just get, their expectation is just getting kicked up or down by some normal amount from their group's expectation. This is what you have to do. Parentheses 1, pipe character. Sarah and I were trying to figure out what the name of this letter is. Pipe character, that's what it's usually called the other day. And then subject. This is the variable that you're modeling as having random coefficients. And I think it just takes getting used to it. It really, the better way to do it, the better way to come to understand how to construct your own formulas is just to see examples and to gradually catch on. So this is the first example, and then we'll see some more examples, and perhaps it will become gradually more clear what you need to type in, depending on how you're conceiving of, or how you're conceptualizing the data generating mechanism. All right, so where am I?
One final question in the
Yep.
chat box is, so in this case, we assumed that females and males have the same variance. What if they don't?
Well, you can do that too. And that's a really good question. Let's see. I don't know off the top of my head how to do that, but you can do that. If you can't do it with LME4, there are other mixed effects modeling packages. We'll see another example later of another package called NLME, and sometimes one package allows you more flexibility than another in a certain way, and we're going to take advantage of that. For example, for using NLME, it's going to do something that LME4 can't do. And so I would say that's a reasonable thing, and you might want to do, yeah, so one thing is how do you gauge whether or not it's a reasonable assumption that the different groups have the same, that the male variance is the same as the female variance. So you can do some sort of box plots of the people's averages side by side, or, box plots of the females' averages. I would average over each person. Each person has an average value. Each female has an average of their measurements. Each male has an average of his measurements. Even that's not really ideal. So it's hard to gauge. It's an art, I guess I'll say. But people will often err on the side of simpler models and err on the side of assuming sort of common variance. But that's a good question, and you can look into that if you want to venture into more complicated ways of modeling things. Let's see. So I've defined mu f hat, mu m hat. Those are the estimates that came out of the model fitting. So I did LME. Let's see. I did LMER, and I gave it a formula for the random effects model. And this is assuming that the groups have the same variance. And it's fitting everything. It's doing maximum likelihood estimation, or a slight variation on maximum likelihood estimation, I should say. And it's giving me estimates of the group's expectations. And I've got a little line of code that's going to let me compare the true female that I defined was 112, and the estimate was 109.4. The male true expected blood pressure was 128, and the estimate it's spitting out was 128.4. So that's, pretty good estimates there. Now I'm gonna focus on something on this random effects function in this presentation, maybe more than people would in practice, because I think it helps people, it'll help us understand what's happening better. And I think actually it should be more of a focus in practice, and I'll explain why in a second. So fix f of m, that gave us the coefficients for that gave us the betas. Ran f of m is going to give us the b's. It's going to give us estimates of the other coefficients, the random coefficients, which in this case, sometimes people will insist on calling them predictions rather than estimates because they're random, but that's kind of nitpicking. In this case, these are the deviations of the individual's expected values from their group's expected values. All right, negative 6.44, negative 7.208. All right, these are estimates, model estimates, our fitted model estimates of the individual. All right, so subject one, we've estimated subject one is a female. We've estimated the group expectation to be 109.4, and our model fitting is also implying an estimate for this individual's deviation from her group mean. It thinks that her expectation is 6.4 less than her group's expectation. So that's the estimate of that subject's deviation from her group's mean. Her expectations deviation from her group's mean. And here are the true values. Remember, I've got I'm sorry. I'm saving this as subject.effects.hat. So what we just saw from ranf, I'm saving that object. And now I'm going to show you the comparison between the estimates right here, subject.effects.hat, and the true values that came out of that S function, that simulation function. It told us the individual's true effects, their true deviations from their group expectations. So here are the individual's true deviations. Here are our fitted model's estimates of their deviations. So you can see there's a pretty good correspondence in most cases, but in some cases, an individual only had one measurement, and so it's hard to estimate well what that individual's true expectation is. But it's still, you still want to use that data because it's informative for estimating the group's expectations. All right, so let's do this. I'm going to do some plots side by side. One is going to be a plot we've already seen, data and true expectations. Here's the true female overall expectation. These are the individual female's expectations in solid points, and their actual observations, their actual measured blood pressure values are in the hollow points, are represented by the open points. And likewise for the males. Okay, so now that's something in reality you can never plot. You have a real data set. You don't know the red line, you don't know the red dots, you don't know the blue line, you don't know the blue dots. But the mixed effects modeling spits out estimates of the red line and the blue line, and the red dots and the blue dots, every person's estimated expectation. And every group's estimated overall expectation. All right, and I'm getting these, I'm getting these just by taking, for subject one is a female, so I need to start at that person's estimated group expected value, and I need to add the estimated subject effect to that. In this case, it's negative 6.44. So I end up right here. This is my best guess of this subject's based on looking at her one blood pressure measurement along with all the rest of the data and fitting the model. My best guess of her actual blood pressure is this. It's a little bit lower than her measurement. And one way of thinking about mixed effects modeling is to sort of think about it in a Bayesian way and say my prior, the group average is kind of like a prior, and your estimates are based on the repeated values that were taken from that person. This group estimate. You might think of it as empirical based since the prior depends on the data. So your best guess of subject one's blood pressure is not, her expected blood pressure is not to just use the value of her one measurement, really. It's to combine that with all the rest of the data and as a result shrink your estimate toward the female group expectation a little bit. Okay, and so let me reiterate again that these random effects, these sort of subjects' expectations aren't usually of much interest to a researcher. Researchers are looking at, is there a, they're testing things like, oh, is there a difference between male and female? Sometimes these values matter. Sometimes you do care about them. Usually you care about the group's overall expectations and maybe testing for differences among groups. So I'm emphasizing these random effects estimates more than you would in practice because it's part of understanding, thinking through these sort of random effects is part of understanding the data generating mechanism that we have in mind when we're doing mixed effects modeling. And since I'm simulating the data, we can compare the estimates to the true values, and it's just kind of a neat way of assessing how well our model fitting is working. All right, I'm going to go ahead and do the summary function, and as you see here, it's spitting out a p-value for sex male. All right, so this is what you would expect. The sex male coefficient is supposed to be representing the difference between the male overall expected blood pressure and the female overall expected blood pressure. And if you were to assume that that difference is 0, you could do a hypothesis test, and here's a p-value, 0.01. So we have pretty solid evidence against the null hypothesis that males and females have the same expected blood pressure based on this data set. Now keep in mind that there's some controversy over these p-values because you have to make some approximations in justifying the formulas for the tests. And if you scroll up, it'll say t-tests use Satterthwaite's method, and that's one of a handful of ways people have come up with for approximating, for doing approximate testing in mixed effects modeling. Also, you'll see linear mixed effects model fit by REML, and that stands for restricted maximum likelihood or residual maximum likelihood, depending on who you ask. And it's just a variation on maximum likelihood that people tend to prefer in this context, but it's really well beyond the scope of this workshop. All right, what else can we get from this summary object? So, well, summary spat out a lot of information. Let's just see the names of that information. One of them is coefficients. So if you actually wanted to save this value in R without having to type it out yourself, you could do summary of M dollar coefficients to get this table, fixed effects coefficients table. All right, and then you could do row 2, column 5 to get this p-value, for example. All right, so anyway, that's how you might just pull the p-value out of the model summary. actually, if you look, you also see a sigma, and that's familiar from summary of M. If M is an ordinary linear model, sigma is the estimated error variance, and that's what it represents here also. So what was the estimated error variance? 5.15, that's what the model came up with for its estimate of the error variance. Well, what was that? What was the one we actually used in the simulation? 6. A pretty decent estimate. And remember, that's error variance. That's deviations of blood pressure from an individual's expectation. What about the deviations of the individual's expected blood pressures from their group expectation? What about the standard deviation of that normal distribution? Well, you can also get that standard deviation, and the command for it is a little bit complicated. I don't know of a simpler way of getting that estimate out of this object. But anyway, this will give you the estimate attribute of the summary object $varchor $subject is what got it. And you can just sort of go step by step and say, what is, okay, there's something called varchor. If you really want to try to figure out what exactly is happening here, you can go step by step and say, what is summary M varchor? And you get this, and it just looks pretty simple, but actually getting these numbers out of here is a little bit complicated as far as I can tell. All right, so anyway, that was the estimated groups standard deviations, 9.4. And the value we actually used for generating the I should say the subject's expected values as deviations from their group's overall expectation, the variance we actually used, or the standard deviation we actually used was 7 rather than 9.36. So again, it's pretty decent. I mean, think about how little data we have. We have 1, 2, 3, 4, 5 subjects from one group, 1, 2, 3, 4, 5, 6 subjects in the other group. They have 1 to 4 measurements per subject. This is really not much data. So I think it's quite a credit to mixed effects modeling that these estimates are quite nice, because it's making the most, when you're bringing to bear an accurate assumption or an approximately accurate assumption, then you're really going to squeeze as much information as possible out of every ounce of data that you have. Okay, conf int. If you might guess from the name, that's going to be a confidence interval. So this is the function that will give you confidence intervals of the model. So I figured out that the best thing to do is add a little parameter here that says old names equals false. Otherwise, I mean, you can try it without, but here's CI. Okay, so there's a confidence interval for sigma. We've got an estimate. We saw our estimate earlier. If you want confidence interval, here you get one from conf int. There's a confidence interval, 95% confidence interval for sigma. For the intercept, which is, remember, is the female group overall expected blood pressure measurement. For sex M, this is, remember, the difference between the male's expected blood pressure measurement and the female's expected blood pressure measurement. So we've got a bunch of nice 95% confidence intervals here. And SD intercept given subject, that's the other thing. That's the only parameter left. It's the standard deviation for drawing the individual's deviations from their group expectation. So we have an estimate of 9.36, and here's a 95% confidence interval for it. Now, if you don't do old names equals false, in my experience, it just sort of, what it shows you on the left-hand side here, it's hard to know what parameters it's talking about. So for some reason, that's necessary for this table to actually be sensibly labeled. Okay. Now, if you wanted to, we've already tested maybe that one of the fixed effect coefficients is 0. Now, you might also test whether or not one of these a random effect is actually needed in the model. Now, what would it mean to drop out a random effect? Well, you could say that I don't need every female, their true expected value of blood pressure is the same. All of them have true expected values on the red line, and their actual draws are just normal deviations from the red line. If they have repeated measurements, then their draws are normal deviations from the red line. Same with the males. Their true expectations are all right on the true line, but you take their blood pressures at various times, and they're just going to deviate from their expectation, which is equal to the true line, by some IID normal 0 sigma squared errors. Now that's a really unreasonable assumption in this case. But if you wanted to test it, RANOVA is the command. I think this is from the, I don't know if this is from the LMER test function or from the LME4 function or library, but RANOVA, it's ANOVA-like table for random effects, random ANOVA. And here's what it says. If you were to drop the 1 colon subject term, if you just treated the draws, treated all males as having expectation equal to the overall group expectation, and then you looked at this data and you calculated a significance probability of that null hypothesis. Here's the p-value right here that you would get for a particular way of doing that test, 0.003. So that's strong evidence that dropping this term wouldn't make sense, wouldn't square with what the data actually looks like. You could also look at the AIC values. If you like AIC criterion for model selection, here it is right here. The original model has an AIC, the model you already fit has an AIC of 145.57, and lower is better for AIC, is that right? So if you dropped out your random effect, your AIC would be 152.25, which is higher, which is another indication that it's maybe a less preferable model. All right, so that's example 1. Oh, well. So let's see example 2. And we're not going to spend as much time because we've got, we're getting the hang of it. Oh, here we go. So here's another scenario. You've got a number of schools that you're interested in. Well, okay, I shouldn't start with the schools. We're interested in the relationship between SAT scores and parents' income. And usually when you're dealing with income, you want to deal with log income because income is a very right-skewed distribution. So we'll use log income, maybe log base 10 income to make the numbers make sense for our, that's going to be the explanatory variable. And we're going to look at log of income and SAT scores of students. But let's say we're going to look at students from a variety of schools. We're going to take a handful of students from each of a large number of schools and think about the overall relationship between SAT scores and parents' income. Now let's assume that there is a true line relating SAT scores and students' income. And let's also assume that every actual school has its own line that deviates from the true overall line by some amount. In particular, its slope deviates from the overall line by some amount, and its intercept deviates from the overall line by some amount, and that those deviations can be modeled as normal. Would it be reasonable to think of some overall sort of true overall expected relationship between SAT scores and parents' income, log income? There's some true line where the higher your parents' log income, the higher your expected SAT scores. But any individual school will have its own line that may differ from the true line by some small amount that could be modeled as normal draws. In particular, every school's slope is going to differ from the overall slope by some normal draw. Every school's intercept is going to differ by the overall intercept by some normal draw, and those deviations are the school effects. Now, a school's slope and intercept deviations should not be considered to be independent of each other. That would be a huge mistake to think that which it doesn't. I mean, you're not sort of the modeling isn't going to think that you mean that, but just to have it clear in your mind, that's not generally what you would assume. The only way you would assume that a school's slope effect and intercept effect are independent of each other, the only context in which that would be reasonable would be if the mean is approximately 0. The mean of the explanatory values is approximately 0. All right, so this is still pretty abstract, so we'll just sort of get to the plots in a second here. If you really want to look at how the model would be written out, YI, the ith SAT score, let's say that the ith SAT score measurement came from, oh no, that should have been a J instead of a K right there. Oh no, I'm sorry. I've got some similar examples that I'm conflating. So no, I had this right. Okay, the the ith SAT score, the ith student's SAT score is going to be on a line. Well, its expectation is on a line. It deviates from that line by some normal error, but that line has as its intercept the overall intercept of all possible students in all possible schools, plus some little effect attributable to that school. That school tends to have, let's say, higher or lower SAT scores than other schools, than the average school. And furthermore, that school has a slope, a coefficient of xi. Xi is log income. That school's slope deviates from the overall slope by some amount that's specific to that school. So some schools have a steeper slope of relating income to SAT score than others. That would be a reasonable thing to think. So every school has its own BK-CK pair, and they are drawn normally. And we're just going to think about the schools are independent of each other, let's say, but a school's intercept and slope should not be assumed to be independent. They are a draw. The BK-CK pair is a draw from a bivariate normal with some unknown covariance matrix, 2x2 covariance matrix. All right, here's another diagram. It's going to be a diagram for each one. So the overall expectation, if you didn't know anything about schools, if you just had a student's parents' log income and you wanted to estimate their SAT score, you would just sort of think, well, this is a good equation. There's some overall slope, some overall intercept, defining some overall line. But any given school, which I'm calling cluster here to be a more general, any given school has its own effect on intercept and effect on slope. And let's say there are n schools. All right, so the expectation at school 1 is actually going to follow a slightly different line. Once you know that they're in school 1, there's a different line. It's mu int plus the random effect of intercept for that school plus mu slope plus the random effect of slope from that school and times x. So that school's intercept is mu int plus b1. That school's slope is mu slope plus c1. And the actual observed SAT score values, well, this is just the expectation, but from one student to the next, they're not going to fall exactly on the line. So one student takes the SAT and they've got an expected value based on their school and their parents' log income, but their actual value, they don't fall exactly on the line. They deviate from the line by some, let's say, IID normal errors, normal 0 sigma squared errors. So student 1 got this SAT score. Student 2 got this SAT score. Student 3 got this SAT score, and they're all from school 1, so that's why they're deviating from this same line, the line corresponding to school 1. But then you go all the way to school N, and there's a different line. And the capital N, let's say, capital N is the total number of actual observations. The capital Nth SAT score, if the capital Nth person came from school lowercase n, then you just need to think that there's some normal draw, some normal 0 sigma squared draw kicking that person's SAT score off of their school's line of expected SAT scores. All right, back to the script. So I'm going to do 30 schools. So some of this is not really important. I don't want the schools to have the same average SAT scores or as average parents' log incomes just because it's unrealistic. So part of this code for simulating the data is doing that, and it's not really important for the modeling. It's just kind of just makes the data a little more realistic. So I'm just going to kind of gloss over. I'm going to gloss over the simulation code here because it's a little more complicated, and a lot of it really isn't essential to what's happening. So let's just, but realize if you want to play around with things, you can mess around with these numbers. I've got 30 schools. I've got somewhere between 10 and 15 SAT scores that I'm going to be taking from each school. Let's just kind of skip to the data here. Skip to the plots, I should say. And there's quite a large chunk that needs to be run that isn't essential enough to spend time on right now. Here's what was simulated. I've got a thick black line representing the true mu slope mu intercept line. All right, a true mu intercept mu slope line is in black. Every school, there are 30 schools, every school has its own line that deviates from the true line. Its intercept deviates by some normal amount, its slope deviates by some normal amount, and I'm in fact, those deviations are not independent of each other. Although the school's lines are generated independently of each other. But a given school's slope and intercept are not independent of each other. Our slope and intercept deviations from the black line are not independent of each other. All right, what if I add the data to the picture? All right, so here are the actual SAT scores. There's the actual overall true underlying relationship between parents' log income and SAT score, the thick black line. Any given school has its own relationship that differs from the thick black line somewhat, and we've got code that's drawing every school, all 30 schools, each one gets its own line. And when you actually measure SAT scores, you just get these points, and I'm coloring them by school. So, well, let's just see the data only. In reality, this is what you see. You don't see the true lines. You don't see any of the true lines. You see a big scatter plot of points, and you can color them by school. Honestly, if I saw this data set, I would think, oh, there's almost no relationship. But it really looks like a sort of a centric, spherical shape. But there's a little bit of a slope to it, and it's really hard to make much of the colors. You wouldn't really think that you could tell whether or not different schools have different relationships just by looking at the scatter plot. Well, for one thing, there's too many. There's so many schools that it's a little overwhelming, but all right, so is that clear? We've got 30 schools. Every school has its own true line. There's an overall true line that the schools deviate from. And when you take 10 to 15 students from each of 30 schools and you record their SAT scores and you draw the plot and their parents' log income and you draw the plot, this is what you, and you color by school, this is what you might get. All right, so how does our mixed effects modeling formula differ this time? So last time, I would have said, oh, every school has its own coefficient, has its own sort of intercept deviation, or every subject had its own intercept deviation. So I had a 1. I had a random effect. All right, so log income, that's the quantitative explanatory variable, and we're pretending there is a true line. The 1, there's also a 1 here that's implicit. There's a true slope and intercept overall. And every school gets a random coefficient, gets its own random coefficient of log income and its own random coefficient of 1. But that's implicit. Even in the random effects term, you don't have to put 1 and it assumes 1. If you didn't want to have an intercept, you'd have to do -1 if you didn't want every school to get its own random intercept. But every school gets its own random coefficient of log.income and coefficient of 1. And the parentheses of log.income pipe school is the term, is how you specify that term in your formula. All right. So I ran the LMER and it did the fitting. What does it give me for fixed effects estimates? It thinks that the black line's intercept is 880.8, and that the slope of the black line, the thick black line, the true overall relationship was 43. So I'm just gonna give those mu.int.hat, mu.slope.hat, and call those descriptive names. Let's compare those to the truth. Wow, okay. Here are the true values from my simulation. I had to do a little work to get these true values. So if you really want to dig into that code, you can. But here are the true values from the simulation. The true intercept was 882, and the true slope was 40 for the black line, and my estimate was 880 and 43. 880 intercept, 43 slope. All right, what about random effects? Ran-F of M. Well, there's a lot. Every school has its own deviation of intercept and its own deviation of slope of coefficient of log income. Right? These are the B's and C's. Every school has its own B and its own C. Its B and its own C. One has a B1 and a C1. School 2 has a B2 and a C2. That's what these values are representing. They're representing estimates of B school 1's intercept effect, school 1's slope effect, school 2's intercept effect, school 2's slope effect. Now I can also, well, okay, let's save them as more descriptive names, and I can just line them up next to the real values because again, this simulation function that I ran gave me the real effects, that are built into those lines that you saw in the plot. I know the real effects, and I can compare them, and sometimes they're pretty close, sometimes they're quite a ways off, but that's the nature of data and randomness. And you can compare the school's true slope effects to the estimated slope effects. And I can do another side-by-side plot here where I do the true lines and overall expected line and the lines you get from mixed effects model fitting. This is the black line. That looks pretty remarkably accurate. Yeah, and it is because we saw the numbers. And again, the black line is usually the only thing you care about. You never see these true lines. You can draw the estimates of the school's true lines if you care about them, which, I mean, they're in this context, actually, that could be realistic. You might try to identify why different schools have different slopes. Why do some schools, why is it that at some schools the effective log income on SAT score isn't so strong, and at other schools it's a very steep line and it is strong? So you might care about that in this context, but usually the thing that you care most about is the black line, and the other lines are sort of a means to an end for estimating the fixed effects. I've got another little plot here that I'm going to run it just for the heck of it. It's more of a sanity check than anything. So let's see. Every school has its own true intercept and true slope. And I'm drawing those as diamonds here. There are 30 solid diamonds, one for every school. It's got its own intercept and its own slope, and I know them because they were used in simulating the data. And I'm also drawing points of every school's estimated slope and intercept and coloring them the same color, just so you can kind of see if this is another way of trying to check whether these things are lining up, because it's hard to test. It's hard to look at this picture and say, oh, this orange line this orange line kind of looks like it's a decent estimate of this orange line, but it's kind of cluttered. So just another way of trying to look at that. And actually, this was more of a sanity check also for making sure that the optimization was actually working within the LMER function. And I will that for this data set, or for this scenario, if you change the parameters around a little bit, you could very easily run your LMER function and get an error message, or at least a warning message saying that there were problems with the optimization function algorithm, and it may not have hit the true likelihood maximizer. And that sort of thing, in my experience, that sort of thing is actually fairly common in mixed effects modeling. So it's not just sort of an abstract concern that, oh, this is a non-convex optimization you're trying to do, and you might not hit the truth, you might get stuck in a local optimum that's not the true likelihood maximizer, and then all of your inference is invalid and your estimates aren't any good. It can actually happen. And I believe usually when it happens, there's the function will spit some warning message or error message out saying that they suspect that you didn't really get the true maximizer. But it's good to make plots like this, for example. I mean, I don't know it depends on the context. Sometimes it's really hard to make plots that, but just trying to visualize the random effect. Okay, so you can't make plots like this because you don't have the true values, but you could just make the scatter plot of the estimates. And if they all, for example, were perfectly along a line, which is something that did happen to me when I was playing around with this, I made this plot, and all of the dots, all of these open points were perfectly along a line, and I thought, that's probably a false probably not actually hitting the right optimum. It's hitting some fake optimum that's like a lower dimensional in a lower dimensional subspace. So it's something you have to worry about. And I would say, don't worry about it right now too much. It's good to be aware of the possibility of optimization failing in mixed effects modeling. And if it happens, then sometimes you can fix it by using a different optimization algorithm internally. And what that will look like is something like, well, you'll see an example of that in the solutions of one of the exercises in this mixed effects model solutions file. But what that looks like in practice is, let's see, where am I? I went too far. Hey, where did I do the fitting? Here we go. LMER, you'll have an extra parameter that says use a different algorithm for doing the optimization. And you can just try different algorithms and hopefully one will actually work and not get stuck in a local optimum. And you can look at the help file for LMER to see how to specify different optimization algorithms and which ones are available to you. All right, so I guess I'm right here. Let's look at the summary. So what's the significance probability for the test that the true line's slope is 0? Right here, very tiny, 0.000033. And you want to pull out the p-value, here you go, just like last time. And if you want to see what is the estimate of sigma, the error variance, that means the draws of SAT scores from the school's true line, from each school's true line. There you go. There's the estimate, 111.4. What was the one we actually used? 100. That's pretty close. And and then I've got, last time we had standard deviation, the standard deviation of the group's effects, of the subject's effects. This time, like I said, every school has its own intercept and its own, or intercept effect and its own slope effect, its own deviations from the overall intercept and its own deviations from the overall slope. So in this case, you don't just have a single standard deviation and you don't just have two standard deviations, you have a covariance matrix, because we're allowing the possibility that that slope and intercept are correlated. And that is a very good idea to allow for that. And it's default, so it's not something you have to worry about. It's automatic. It's not going to assume the simplest way of writing the model up above does not assume that the coefficient of 1 and the coefficient of log income in the school random effects are uncorrelated with each other. And here is its estimate. Here is its estimate of their variances and their correlations, their correlation with each other. I should say covariance with each other. So this is the covariance matrix of the BC pairs. All right, so right here, B1C1 through BNCN, these intercept slope effect pairs, there's one drawn for every school. and we're assuming they're normal with mean 0 and some unknown covariance matrix. And here is the estimate of that covariance matrix. And here's the actual covariance matrix. I called it, see, I calculated it above, and it's a little bit complicated to calculate in this case. I mean, not too bad, just not worth not the focus of today's workshop. So anyway, it's actually it's wildly overestimating. So don't know if that's something to be concerned about or not. Maybe it's just, it's hard to estimate covariances. So I don't necessarily think it's an indication that something's going wrong with the function. But anyway, you get the estimate. You can compare it to the truth in this case. In reality, all you have is the estimate. You don't know the truth. Let's look at the confidence interval for, well, let's just look at the confidence interval for the fixed effects. All right. So I'm doing confident again, but I'm specifying the parameters that I want the 95% confidence interval for. And so here's the confidence interval for the black line's intercept. Here's the confidence interval for the black line's slope. And again, the estimates were right here, 880, 0.8, and 43. The confidence intervals are right here, confident. And once again, we can think about simpler models. Well, we've already sort of thought about a simpler model by a model that doesn't have a coefficient for log income, and we saw a really tiny p-value for that case. You can also think about maybe all schools have the same line. Should we just pretend that all schools have the same line? That would be a RANOVA of the model. RANOVA will say, what if I drop that? Actually, it doesn't go all the way. It's not saying what if they all have the same line. It's saying what if we drop the log income effect in this random effects term. So maybe they don't have different intercepts, but they do have their own random slope effects. Well, we can't really rule that out. That's not a very small p-value, so we don't have strong evidence from the data that the schools actually do have different slopes, because there are only 10 to 15 draws per school. So, and there are only 30 schools. And we can compare AICs, and actually, so my comment here says that the removal results in lower AIC. That's from a previous version of the data. I guess I've changed the parameter since then. So actually it results in higher AIC, but it's not something you can rule out with a hypothesis test. You can't rule out the idea of dropping log income. So actually, let's do another form of this RANOVA. If you actually want to consider dropping log income, and also what happens if you drop log income and drop the C's and the B's, let's say. You can get that by doing reduce.terms equals false, and I guess you can look into the help file for exactly why this is doing what it's doing. But if you, but anyway, this option says, okay, just go all the way. What if you go all the way and you throw out the entire random term of the B's and the C's? Well, that really, really is not indicated. There's a very, very tiny significance probability of that the data would look like it does if there were no random effect terms. In other words, if all schools had the same true line. And you can compare AICs as well, getting higher AICs by dropping those. But we did see that maybe it's okay to not have different slopes for log income for different schools. So we could redo the fit and say we're going to give every school a random effect for the intercepts, but we're not gonna allow for differences in slope. We're just going to say all schools have the same slope. And that's how you would do that model. And you get new estimates of the fixed effects, meaning the slope and the intercept overall, and it's a little different. Now it thinks that the slope is 43.9 instead of 43.0. That's not too big of a difference, honestly. And you can compare this. It's doing worse though. It's slightly worse when we make this assumption rather than using the true model that I actually use, which is giving different schools different slopes and different intercepts. All right, random effects. Every school has its own intercept effect in this case now, because this is the new model. We redid the fit, and we did not allow for different schools to have different slopes. We gave different intercepts. So here are the estimates, and you can compare the estimates to their the true values, and you can make the plot of, well, because we know the truth, we can make the plot of these were the true lines, and these are the estimated lines that you get with mixed effects modeling, while assuming that all of the lines have the same slope rather than allowing them to have normal deviations in their slopes.
Good.
Was that a question? I couldn't really hear it. All right, maybe it was a mistake in audio. So if if you have come to prefer the simpler model, then you kind of need to go back and redo your fitting, redo your summary, and again, you get a tiny significance probability, so you still aren't tempted to think that the true slope of log income is 0. Redo your RANOVA. All right, so anyway, that's another example. That's different groups or different clusters have their own true line relating to quantitative variables, and those lines deviate from some overall true line with some normal deviations in their slope and intercept. All right, so we'll try to make it through the third example at the very least. I know we're pressed for time, but I mean the point here is just getting the idea. The main point is getting an intuition for what mixed effects modeling is. It is usually assuming that there are some extra normal draws that are happening along the way in between the original things that you're trying to estimate and the observations that you're getting. Like there's an extra layer of normal draws between the thing you're trying to estimate and the thing that you're actually measuring. All right, so now we're sticking with SAT scores, and now we're gonna have even more layers. You could call this hierarchical modeling. Really, they're all hierarchical modeling though, but this would be more likely to be called hierarchical modeling. So we're gonna have female SAT score average of 1055 overall, male SAT score average of 1042 overall, and every school, so we're not talking about log income, we don't have lines anymore, but we're sticking with SAT scores. Every school has its own effect on SAT score. Every school's average SAT score is going to be some normal deviation from the overall average, and it's going to be the same for males and females. Let's say that. School 1 might be a really good school and might have a a deviation of 100. In other words, the overall female and male SAT average expected SAT scores are 1055 and 1042, but at school one, they're 1155 and 1142. All right, so that's the idea here. But we're going further this time. We're also going to assume that every student has his or her own effect. Every student that we're bringing into the data set that we're measuring has his or her own effect of SAT and has their own expected SAT score. And the actual SAT scores are going to be normal errors away from the student's expected SAT scores. So there's an extra layer going on here. A student, now we wouldn't really need to bother if every student was only taking the SAT once, but we're going to have every student taking the SAT anywhere between 1 and 3 times. So this is like clustering and repeated measurements. This is an extra layer. And I think let's just skip ahead to the diagram. I don't even want to bother with the equation. Here's the diagram. There's a expected female SAT score, expected male SAT score. Every school has its own effect. School 1 has effect B1. So its female's expected SAT scores are the overall female expectation plus B1. Its male expected SAT scores are the overall male expectation plus B1. All the way to mu F plus BN, except I have to use N sub C and N sub S because I've got a number of schools, number of clusters, and a number of subjects. All right, so at school 1, there are, let's say, these 3 students. Student 1 is a female who has her own SAT score effect. Student 2 is a female who has her own SAT score effect, and her expected SAT score is the female average plus the school effect plus her individual effect. Student 3 is a male from school 1. His expected SAT score is the male average plus the effect from his school, the effect associated with his school, plus the effect associated with him personally. That's he's got some expected SAT score, and so on. Now, subject 1, this is her expectation, and her, oops, there's supposed to be plus signs there. Her actual SAT scores, she takes it twice. Takes two SATs. Her actual scores aren't the same as her expected score because, well, the questions are a little different from one time to another, and you get a little bit lucky with guessing sometimes, and you can take the SAT twice and get different scores. All right, so this is her expectation. Her actual scores are going to be deviating from her expectation by these IID normal errors, and we're bringing in assumptions that every school's effect is normal. The school's effects are IID normal 0 with some unknown variant sigma squared cluster. The subject's effects, C1 through Cn subject, are IID normal 0 sigma squared subject, unknown variance there. And then there are errors adding on to the actual SAT, determining the actual SAT scores that you observe. So this has an extra layer compared to the diagrams we've seen before. And well, let's see how to deal with it. And again, we don't really have time to focus on the code for running the simulation, but let's just read in the parameter values, do the simulation, pull out the code. And here it is. Here's the first 20 SAT scores. Student 1 took it twice. Went to school 1, is a female, took the SAT twice, because here's student one. I got a 944, then a 946. That's a little bit of improvement. Probably not worth the extra 50 bucks of taking it again. Actually, I don't know how much it costs these days. It was, I think, 50 when I took it. Student 2 took 1, 2, 3 SATs. Took the SAT 3 times and got these scores, and is still a member of school 1. All right, and you scroll down. Wow, the first 20 are all from the same school. But we've got, we only have 4 schools, and we're doing between 5 and 10 students per school, and between 1 and 3 SAT repetitions per student. All right, so what do we get here? I'm going to draw some plots to clarify what's happening. There's the, see the light blue and the light red, those are the true expectations. The true male SAT, expected SAT score, the true female overall. Every school has its female expected SAT score and male SAT score that differ from the true lines by some effect that pushes it up or down, pushes both the red and the blue lines up or down by some amount, and those amounts are random, are normal 0 sigma squared C draws. I think I'm calling them sigma squared school or sigma dot school in the script here. Okay. And now at each school, we have some number of students whose SAT scores we're going to be measuring. And they have true expected SAT scores that deviate from their groups expectations within their, the adjusted for school. And here we're seeing the individuals. These are the individuals, their expected SAT scores. And their expected SAT scores are varying normally about their group's average, and that group's average is being adjusted by adding the school's effect. All right, and now we're going one step further, and we're taking the SAT. Again, this is the first thing on the plot that's actually something you can observe. All right, I'm simulating with these true values. Everything solid is a true value, and these dots are the actual SAT scores that from these students taking the SAT anywhere between 1 to 3 times, and their actual scores are deviating from their expected scores by some normal, no errors. All right, and just to be more realistic, this is what you could plot. You gather the data. This is what you can plot. You can't plot the true lines. You don't know the true lines. We're doing the true lines for fun because it's nice to simulate things and reinforce the model mechanisms that we have in mind and to compare the model performance with truth. But when you have a data set, what you have looks more like this, and you don't have the nice lines telling you what the true group expectations are, school expectations are, and subject expectations are. You just have SAT scores, observed SAT scores. All right, so how am I going to, so this might be the culmination of the workshop. Maybe we'll work on shortening this and try it again sometime. But or you can, you have the script, you can keep going through it. But I think we're hopefully you're getting the gist of it. But we've got one more line. Oh, okay. We'll do this line and then we'll sort of make sure it's doing something sensible. All right. So the model is that this is a hierarchical model. There's a fixed effect of sex. Every school has its own effect. Every student has his or her own effect. That's how you can encode. That's how you could encode this in the LMER formula. Students belong to schools. Every school gets its own effect. Every student gets its own effect. Now, actually, if you see in the comments here, in this case, you could also just do just have a term that is the effect for student and another term that's the effect for school. That would work fine in this case. I want to warn you that it's not ideal, because if you happen to number students in such a way that they weren't unique, like school 1 had students 1 through 10, school 2 had students 1 through 10, and they're different students, but they've just been given the same number at different schools, then if you do it this way, it's going to think that student 1 at school 1 is the same as student 2 at school 2, and they're going to share a common student effect. So that's a reason to when you know that things are nested in a certain way, to actually incorporate that into your formula. Then you don't have to worry about whether or not these, the various students are being inflated because they happen to be given the same name or label in your data set. All right, so did I run this yet? I didn't run it. All right, well, we'll just look at this output and then we'll call it a day. So here's M. It's saying that, well, here we go. We've got an estimate of the overall female SAT score. We've got an estimate of the difference between the overall male SAT score and the female SAT score. That's usually, these are the fixed effects. These are usually the things you care most about. And you get them, you can get them from summary, you can get them from fixed effects of M. And I guess the reason I also included M by itself here was just to see, students within school and school are the random terms that you're getting. All right, well, we're out of time, so I guess we'll call it a day, and you can finish up on your own. I'll maybe I'll make a shortened version of this, but I think that since from what you've seen and heard so far, you'll probably be able to make sense of the rest of this example and the other example fairly well.